Hi everyone, here is our math problem for today. This is taken from the British Math Olympiad, round number 2, question number 1. And here's the problem. Find all solutions in non-negative integers a and b to the equation the square root of a plus the square root of b equals the square root of 2009. You can pause the video and see if you can solve this British Math Olympiad question. Now let's solve this problem together. Notice that we are after the non-negative integer solution to this equation. This implies three things. Number one, we need to be able to factor this 2009 into integers. Number two, since there are square root symbols here and we want integer solutions, then we need to square both sides of the equation to eliminate the radical symbol. And number three, since we are going to square both sides of this equation, we must be aware of the possibility of introducing extraneous roots. So we need to remember these three steps. All the rest will just flow logically as we solve the problem. So let's begin by solving this equation for b. That means we are going to subtract square root of a from both sides, and we square both sides of the equation. The square of the square root of b is b, and at the right side, we apply the square of a binomial identity to expand the right side. So the square of the first term is 2009 plus twice the product of these two terms plus the square of the square root of a, which is a. Then let's rearrange the terms. We know that b is given to be a non-negative integer. A also is a non-negative integer. Now, in order for the right side to become equal to a non-negative integer, this part here must also be an integer. And since 2 is already an integer, then the square root of 2009 times a must be an integer, specifically a non-negative integer. Because we know that a is non-negative, 2009 is positive, so this square root of 2009 times a must be a non-negative integer. Let's remember this condition. Next, what can we say about the square root of 2009a? As mentioned in the beginning, we must be able to factor this 2009, and luckily, its factors are 49 times 41. And this 49 is a perfect square. Its square root is 7. So we have 7 times the square root of 41a. This entire expression must be a non-negative integer. 7 is a non-negative integer. This implies again that the square root of 41a must be a non-negative integer so that this entire expression satisfies the condition that it is an element of the set of non-negative integers. So let's remember again this condition. Now, for the square root of 41a to be a non-negative integer, what must happen? Notice that we have here 41 inside the radical. To make the square root an integer, we must have a perfect square under the radical. So we need another term that is 41, and this other term must be a perfect square also. So that if a is in the form 41 times x squared, where x is a non-negative integer, then we can now replace this a by that value 41x squared. And 41 times 41 is now a perfect square, and x squared is a perfect square. This means that this entire expression is a non-negative integer again. So this condition for a is very important. Next, now since a and b here can be interchanged without affecting the value of the equation, since this equation is symmetric, then if a is in this form, then b also must be in that form, only that instead of x squared, we have any non-negative integer y for this expression 41y squared. So we can now substitute this expression for a and for b to the original equation. And this is now what we'll have. Looking at the right side, we know that 2009 can be written as 49 times 41. And these are the corresponding expressions for a and b. And so by substitution, we now have this form. So this a now is replaced by this. The b is replaced by this, and 2009 is factored as 49 times 41. Notice now the presence of the square root of 41, the square root of 41, and the square root of 41, and all the other factors are perfect squares. So the square root of x squared is x, the square root of y squared is y, and the square root of 49 is 7, all the rest are copied. And we divide each term by the square root of 41. What's left is x plus y equals 7. And this condition now is what we need in order to identify the solution set for A and B. So we know now that x plus y is equal to 7, where x and y are both non-negative integers. So we can now form this table. We assign value for x and y subject to this condition. If x is 0, y must be 7, so that x plus y equals 7. If x is 1, y must be 6. Again, the sum is 7. And the same explanation for the rest of these pairs. Now, we have the value for x and y, and we know that a is equal to 41x squared, b is equal to 41y squared. So using now this expression, given this set of ordered pairs satisfying the value for x and y, then it's just a matter of substitution. Now, if x equals 0 and y equals 7, then 41 times 0 squared is 0, and 41 times 7 squared is 2009. So our ordered pair AB must be 0 and 2009 when x is 0 and y is 7. The same explanation when x is 1 and y equals 7, we just substitute those x and y values to this expression here. A equals 41x squared and b equals 41y squared. This now gives us these 8 ordered pairs satisfying the equation. But as I have said, since we square both sides of the equation, it's possible that we introduce extraneous roots. So we are going to test each of these ordered pairs to the original equation. And to check them all, here is now the result computed using Desmos graphing calculator. The square root of 2009 is approximately 44.82. Then we substitute a equals 0 and b equals 2009 here. The result is equal to the square root of 2009. So the first ordered pair is correct. For the second ordered pair, 41 and 1476, again, the square root of 41 plus the square root of 1476 is equal to the square root of 2009. So the second ordered pair is correct. In fact, all these 8 ordered pairs are verified to be the correct solution to the given equation. And so we verified that our answer is correct. So this British Math Olympiad is really an interesting Math Olympiad question. Bye for now.